Hi everyone, this is MathsForUni. Today we'll be looking at question 5 from MAT 2019. If you find this content helpful, then please consider liking and subscribing, as well as checking out our full Udemy course. The link is in the description. The question says, this question is about counting the number of ways of partitioning a set of n elements into subsets, each with at least 2 and at most n elements. If n and k are integers with 1 less than or equal to k less than or equal to n, let f of nk be the number of ways of partitioning a set of n elements into k such subsets. For example, f of 5, 2 is equal to 10 because the allowable partitions of 1, 2, 3, 4, 5 are the following 10 allowable partitions that they give. In particular, note that each subset must have at least 2 elements. The first part asks us to explain why f of nk is equal to 0 if k is strictly greater than n over 2. So we have this condition, k is strictly greater than n over 2. Each of our k subsets has to have at least 2 elements. So we have to have at least 2 k elements in our subsets overall. However, 2k is strictly greater than n. So somehow we need to take our n elements and then get more than n elements in our k subsets if we have this condition here. As such, there is no way to do this, and therefore f of nk is equal to 0 in the case that k is strictly greater than n over 2, because each of the k subsets needs to have at least 2 elements. The next part of the question says what is the value of f of n, 1 and y. F of n, 1 looks at the number of ways to write 1, 2, 3, all the way up to n into one subset. If n is strictly greater or equal to 2, then f of n1 is equal to 1, because this is the unique way to have this allowable partition. However, if n is equal to 1, which is allowed at the beginning, we had 1 less than or equal to k less than or equal to n, and so k would be 1 and n would be 1, which does satisfy this condition here. In this case, we only have the 1 element, and so there is no way to put this into subsets because each subset needs to have at least 2 elements. Part 3 of the question says, in forming an allowable partition of 1, 2, up to n plus 1 into subsets of at least 2 elements, we can either pair n plus 1 with one other element, leaving n minus 1 elements to deal with, or take an allowable partition of 1, 2, up to n, and add n plus 1 to one of the existing subsets, making a subset of size 3 or more. Use this observation to find an equation for f n plus 1 k in terms of f n minus 1 k minus 1 and f n k that holds when 2 is less than or equal to k, which is strictly less than n. So in this part of the question, we're going to try and use the statements in the bullet points of part 3 in order to write f of n plus 1 k in terms of f n minus 1 k minus 1 and f of n k. This only will hold when 2 is less than or equal to k, which is strictly less than n. The first bullet point says pair n plus 1, the element on the end, with one other element between 1 and n, leaving n minus 1 elements to deal with, and then we'll have k minus 1 subsets because we'll have one subset corresponding to the pair of n plus 1 with one of the numbers between 1 and n. How many ways can we do this? Well, we're pairing the n plus 1 with one of the elements between 1 and n. As such, there are n ways to do this, and so we multiply n by this f n minus 1 k minus 1 corresponding to this first bullet point. The second bullet point says to take an allowable partition of 1, 2 up to n and just add the n plus 1 onto the end of one of the existing subsets in that partition. The number of subsets will not change, so we'll have k subsets still, and we're looking at the allowable partition of 1, 2 up to n, and so we have an n here. The number of ways to do this is k, because there are k such subsets to add the n plus 1 to. And so we get this formula here. Fn plus 1k is equal to n fn minus 1 k minus 1 plus k fnk. Part 4 of the question says, use this equation to compute the value of f of 7, 3. We can do this by repeatedly applying the above equation to f of 7, 3. If we apply this once, then we'll get 6 f of 5, 2 plus k is 3, and then f of 6, 3. Then we can apply this equation again to find each of these things separately. So f of 6, 3 is going to be equal to, well, n is 5, and so we'll have 5 f of 4, 2, because k is 3, and then the other term will be plus 3f of, and then we'll have 5, 3. However, this thing here is equal to 0 because this 3 here is strictly greater than 5 over 2, using part 1, and so we get 0 for that term there. Then we continue down the chain, and so f of 5, 2 will be next. We'll have, because n is 4, so we'll have 4 f of 3, 1, because k is 2, and then plus 2 f of 4, 2. Next, let's try and find f of 4, 2, because we need it for both here and here. And so we have n is 3, and then we have f of 2, 1, and k is 2, and so we have 2 f of 3, 2, but again, this thing here is also 0. And then next, let's look at these things that we have here, and luckily we notice that we have a 1 here and a 1 here, and so these things are themselves 1, using part 2 of the question. As a result, we get f of 4, 2 is 3, and so a 3 goes in here, making f of 5, 2 be equal to 4 plus 6, which is 10. And then we use f of 5, 2 in here, along with f of 6, 3, which because f of 4, 2 is 3, we have a 3 in here. And so f of 6, 3 is equal to 15. And then finally we use both of these results in here and here to get that f of 7, 3 that we were looking for all along is equal to 6 times 10 and then plus 3 times 15. This is 60 plus 45, which is 105. It was important to use the equation that we have here multiple times to reduce these f's to having lower values in here and here. By the time that we get to a case where k is greater than n over 2, we can get zeros, and then by the time that we get to a 1 being in place of k, we can get 1s, as long as the n value is not itself 1. The last part of the question says, give a formula for f of 2n n in terms of n when n is greater than or equal to 1, and show that it is correct. The question says to show that it is correct to avoid you being able to just write down the answer without doing any working out. If you do provide some working out and you get the answer right, then you'll get full marks. We can take our f of 2n n and apply the recurrence relation to get 2n minus 1, f of 2n minus 2 with n minus 1, plus, and then we will have n f of 2n minus 1 and n. However, this second f here is equal to 0 because n is strictly greater than 2n minus 1 over 2, which is n minus 1 half. And so certainly n is strictly greater than n minus a half, and therefore this f is equal to 0. So we just get this thing here. So let's write that out. We have f of 2n n is equal to 2n minus 1, and then f of 2n minus 2, n minus 1, and then we can repeatedly apply this result again and again. For example, the next step would be 2n minus 1, and then we would have a 2n minus 3, f of 2n minus 4, and then an n minus 2. This is because we're just using this formula again here, but putting an n minus 1 in here, and hence everywhere else on the right-hand side. Therefore, we can repeatedly apply this formula to get 2n minus 1, 2n minus 3, all the way down to 3, and then the final factor would be f of 2, 1. At this stage, we couldn't apply the recursion relation again because we would get a 0 here and also a 0 here. Instead, we directly compute f of 2, 1, and as we noted in part 2 of the question, this is equal to 1. Therefore, we have 2n minus 1, 2n minus 3, all the way down to 3, and then times by 1. This is acceptable as a final answer, but this can be tidied up by noting that this is equal to 2n factorial and then filling in the missing numbers. In particular, we have a 2n here that is missing, and then a 2n minus 2 here that's missing, and so on. In between each of these factors, we have a missing factor all the way down to 4 and then 2. We can then take a factor of 2 out of each of these things here, and we'll have 2n all factorial divided by 2 to the power of n, because there are n 2's to come out of these, and then we're left with n minus 1, all the way down to 2 times 1. And this gives us an n factorial. We have, again, n minus 1, all the way down to 2 times 1. This is a tidier representation of the same product, but either answer is acceptable. If you've enjoyed this video, then please consider liking and subscribing, as well as checking out our full Udemy course, of which the link is in the description. Thanks for watching, and goodbye for now.